Okay, so we have a buoyant blob of fluid, an ambient fluid, which is set into rotation at a rate, let's call it omega. And we've conceded that rotation is going to make the buoyant blob move along the rotation axis. So just imagine there's no gravity, and if the rotation is high enough, it will dominate the hydrostatic pressure, so this will happen. So you have rho minus delta rho inside and rho here. We have surface tension sigma. So this is basically the same analysis, but with bond number negative. Okay, so if we recall for a puddle, we argued that a puddle is going to be flat everywhere, and then just have these little regions at the end where curvature forces can balance hydrostatic pressure. The same is true here. You basically get a cylinder with spherical caps. Okay, so we can then write down the system energy. So it's going to have a rotational, so a kinetic energy component and a surface energy component, and then we're going to minimize it, and that'll give us the length of the drop. Okay? So drop energy ½ J, so this is the angular momentum. And we assume again that the whole thing is in equilibrium. So once it's decided what shape it wants to take, there's no dynamics. So everything's in solid body rotation. Okay, so this is the rotational kinetic energy. And this is the surface energy. And if this drop is sufficiently long and thin, then we can ignore the ends, right? Because they're going to scale with this length to this length. Okay, so V equals pi r squared L. So L is our length, R is the radius. And the moment, this is the moment of inertia. So for a cylinder is r squared over 2. Okay, so then the energy per unit volume So we divide through by volume. and then we can find the shape that minimizes this energy. Okay, so this will be minimized. Okay, so this gives us the radius, the drop radius, which minimizes the system energy. Okay, so whenever one does calculations, one wants to try and learn see what insight one can get into the problem. So, and one also wants to make sure that it's consistent with your intuition. So first off, we see that the higher the rotation, the smaller the radius. That's consistent with what we expect. We also see that the higher the surface tension, the larger the radius. And that also makes sense because it's surface tension which is acting to resist the deformation due to the rotation. Okay, so if we want to get things in terms of the volume, then we can express oh, wait a second. This should be cubed. Yeah, cubed. Yeah. Okay, and so this tells us that the surface tension we can express. So this is, after all, surface tensiometer. This is a device for measuring surface tension. We want to be able to express it in terms of the system parameters. So 4 pi 3 halves, and then we have delta rho omega squared V over L to the 3 halves. And this is Vonnegut's formula. Okay, so for you put a drop in with density anomaly delta rho and you rotate it at speed omega, so a drop with delta rho and volume V, then you measure the length and so infer the surface tension. Okay, and the nice thing about this technique is it basically isolates the drop. Normally when you're measuring surface tension, there's some interaction with rigid boundaries, and so this complicates matters. So here you really just have a fluid suspended in another fluid, so one doesn't need to worry about complications from rigid boundaries. Okay, so there are many such problems where you basically write down the surface, the total energy, and minimize. So the next so the next thing I'm going to do is so I'm going to spend half of today's class and a little bit of next class actually doing the dynamics. So this is really a canonical problem in interfacial flows. So this is capillary rise. So we've all seen this. So these are different capillary tubes of different diameter, and we're going to basically submerge them in the same fluid. And we want to be able to do two things. We want to say predict the final rise rate, and we also want to be able to predict the dynamics. So what sets the speed of the front? Can we solve this problem completely? And we can. Okay? We see that the smaller tubes on the right give rise to greater ascent, and but the flow slows down towards the end. Okay? And for that matter, so that's the sort of classical one. But there are others where, so here we expect there to be a balance between surface energy and gravity, but you can also have a tube going in horizontally, in which case gravity is not a player. But we'll also see how that one works. Okay, so so we want to rationalize what we've just seen. Okay, and then this is a huge problem for capillary rise with all sorts of applications. So people who in petrology who are interested in oil or water moving through porous media. So you have, if you're pushing oil with water, then you have an interfacial tension at the edge, at the interface between the two. And this is, if you're pushing it through groundwater, then you have very small constrictions. So this sort of capillary dynamics is hugely important and in fact determines the rate of flow to a large extent. So okay, so and this also arises throughout biology. So drinking strategies of many birds and insects rely on capillary action. So for example, the tongue of a hummingbird is shaped like a tube, and it basically goes into the fluid, and the fluid rises spontaneously and fills the tongue up. Then it extracts its tongue. So whenever you're looking at groundwater flows, surface tension is a big player. Okay? So if we look at the history, so Leonardo da Vinci he discussed this capillary rise. Suggested again that mountain streams are fed by sort of capillary wicking of rainwater. Okay, so Borelli Oh, we should put Da Vinci's dates, 1452 to 1519.
This is a silly question, but capillary rise from underground water or?
Yeah, so from rainwater, say.
It's
Yeah.
a little bit underwater.
Yeah. Okay, so Borelli did the first experiments, and he basically observed that the height goes as 1 over r. Question?
No, so we were wondering about the height of that and whether you could use it as a pump actually regarding the magnitude
What was that?
conjecture.
Was that?
We were wondering if you could actually use it as a pump, right? Because
Well,
you would have to strike it too, like the hummingbird, right?
I mean, it will. You can imagine. I mean, people have hypothesized that. I mean, it's wrong. It's wrong to an extent, but the rise of sap in trees is through capillary action. So there's basically a low pressure associated with the curvature of the tube, which basically opens onto these very small openings on the leaves, and they're suggesting that pressure is sufficient to draw fluid all the way up. But it's a little more complicated. But it's certainly possible. I mean, you are getting pumping, right? I mean, basically this curvature pressure is driving flow. Right? Okay, so this is actually called Jurin's law. He was a physiologist. We didn't know the work of and this is now known as Jurin's law. Okay, so let's look at the I mentioned actually Hawksby looked at this problem, and his work was reported by Newton, but no credit was given. But let's think about this problem. How do we actually solve it? First off, how do we rationalize h going as 1 over r? So again, we've seen that there are many ways to look at these surface tension problems. You can look at energetics, you can look at pressures, you can look at forces, and this one is again worth looking at from various angles. So we defined a spreading parameter. So our spreading parameter determined whether or not a fluid placed on a solid would spread. So if we have a fluid so we have this tension, which is gamma solid vapor. We have this tension, which is gamma solid liquid, and then we have the third one, which is gamma liquid vapor. Okay. So the spreading parameter is defined in terms of these three tensions. Okay, so it's basically this one minus these two. Okay, so it's going to spread if this thing wins. If you like, right? It's basically if the energy of the dry surface is less than that of these two wet surfaces, then it's going to stay as it is. Right? Okay, but we have a slightly different picture when we're looking at capillary rise. Because notice as this thing moves, you're creating two surfaces, right? You're creating this surface, this new wet surface, and this new surface. So you're actually creating two surfaces, whereas in capillary rise, you're not. So in capillary rise, you're just creating, all that matters. So if this thing moves up or down, this surface isn't changing, right? So that's equivalent to this one not changing, right? So all that matters is the relative magnitude of this energy and this energy. Okay? So, let's try and be consistent here. So this is gamma solid vapor. This is gamma solid liquid. And then we have our green one, gamma liquid vapor. Okay. And then we know that this contact angle is prescribed by the relative magnitude of those three tensions. Okay? Okay, so now we need a different parameter. So the spreading parameter is not relevant here because, again, as this thing moves, it doesn't change. This energy doesn't change. So we're going to call this an imbibition parameter. Okay, so we're basically removing this one from consideration because that interface, that energy doesn't change as the thing moves up or down. Okay, and we have from the definition of the contact angle, okay, so this, whether or not the thing spreads, so whether or not the thing climbs, depends only on the surface tension, which is basically this guy, and this guy, which contains the information about the other surface energies. Okay, so okay, so I've stated this, so it's worth writing down. So the motion of the interface doesn't change the interface's energy. Yep.
Explain that again. Why?
Okay. So, because when you're trying to decide, when you're looking at imbibition as opposed to spreading, so here they're basically, if this thing's going to advance, right? So let's just say this is a wall here, right? If this thing is going to spread, then you're creating new wet surface there, but you're also creating two interfaces, right? You're extending the extent of the wet solid, and you're also creating more of this interface, right? Right, because this thing's stuck here, right? We're just saying, is it going to move? And that, if it moves, then you have to create this interface as well as this one. Okay?
Otherwise, there's more than if it's nice.
Yeah, yeah. Whereas here, this thing moves up and down. This doesn't change, right? So the energy of this doesn't change. All that matters is the amount, the extent to which you're wetting.
It's infinite. They are the same thing.
Yeah, yeah.
If it's infinite, it wouldn't matter.
Yeah.
Okay.
Okay. Okay, so our condition for imbibition then is simply that I is greater than 0. So inhibition condition, let's say when will fluid go into a pore, simply that I be greater than 0. And since we can relate I to the spreading parameter, so it's this plus this guy, and this is always greater than 0, we can see that things will imbibe much quicker, much more readily than they will spread. What? This? No, no. But all of these surface energies are positive, right? I equals... No, it's plus, right? To get from I to S, you have to... Right? This is smaller. This is smaller by this amount. There's a minus here, right? So you have to add this one to get this one.
Okay.
Yeah. Okay, so this imbibition condition is always easier to satisfy than the spreading condition. Which is at S equal to 0. Okay, so while complete spreading isn't that common, most fluids will go into sponges and so forth, right? Okay, so let's look at the energetics now. So let's try and rationalize the height of rise. So what happens if we've argued that if I is greater than 0, then it will imbibe. So if we put a tube into a fluid, okay, so this is the case I greater than 0, so the fluid climbs. Okay, and if I is less than 0, that is to say the contact angle is on the opposite side of pi by 2, then the fluid sinks. Okay, so one can have both situations just depending on this I parameter. Okay, so we look at the energy of the column. So again, we're going to write down the energy of the system. It's now going to be gravitational potential energy and surface energy, and we're going to minimize it. So all that matters is the wetting energy on the walls, because again, this thing's not changing. Likewise here. So what matters is the length of the column. And then, so that's the surface energy. And then we have the gravitational potential energy, which is gravitational potential energy. Okay, so this is, we can express this in terms of I. Okay, so this is going to be a minimum when dE by dz is equal to 0. Okay, so let's call the height at which the energy is minimized h. So this gives us or 2I rho gr. So this gives us Jern's law. Okay, and so we can see that if we plot these two energies, so this one's going as z, so this is minus, that's going as minus z, and this one's going as r squared, or sorry, z squared. So the surface energy is going like this, and the gravitational potential energy is going like this. And so the total energy is I did a rubbish drawing. Let's do that. At least it looks respectable. So then so the total energy is then doing something like that. Okay, and this is this then defines H. Okay, and so okay, so we see in fact that the rise height depends on the surface tension, the contact angle, and the radius of the tube. And this is consistent with Jern's law. So in fact it is quite nice in that, again, we know what the surface tension is, and we know what the contact angle is. you're basically done. So you can predict its height, because this is simply that. Okay, so let's try and understand that. So we got that from the energetics. It's also simply seen by looking at pressures and forces. But let's, again, try and extract as much physics as we can from the mathematics. Okay, so our result there for H, that describes both capillary rise and capillary descent, because the sign will change with theta E, right? So with the equilibrium contact angle, this is always going to be positive, but this can change sign according to whether the equilibrium contact angle is greater or less than pi by 2. Okay, so it depends on whether the equilibrium contact angle is less than, greater than. Okay, and we see also that the height increases as the equilibrium contact angle goes down, and we have the maximum height for theta equals 0. Okay. So that makes sense. That's the fluid is that when the tube is most, say, hydrophilic, water will climb most readily. Okay. Okay, let's leave that for now. Okay, so let's do a pressure argument. Okay, so now that we've established that this rise height only depends on this surface energy and the contact angle, let's just keep those, and we'll call this sigma, and this is theta E, and this is R, and this is height. Okay, so let's look at a couple of points here and calculate the pressure. Okay, so we know that we have to be able to get to this pressure either by coming along here. So we know that the pressure at B is going to be atmospheric, right? Because we're crossing a flat interface, so we get nothing there. And it's on the same height as this. So this is going to be atmospheric here. And so as we go up, the pressure is decreasing. We get suction, as in a meniscus. And so then that takes us to the point A. And so that height there, so the hydrostatic pressure change as you move along there has to be exactly equal to the jump associated with the curvature of the interface. Okay? Okay, so now there's one thing we have to do. We have to assume that, so if R is much less than LC, the capillary length, then the top surface will be a spherical cap. Okay, so we'll always, if saying that the interface, the top surface is much less than the capillary length, is saying that gravity doesn't come into play. So if gravity comes into play, then you have to consider its influence on the shape. But if not, it's basically going to act to minimize the surface energy. So you're basically going to get the portion of a spherical cap which has the right contact angle. Okay? And so that gives you this result for the radius of curvature. Okay, that's P at A, so at this point here, is going to be atmospheric minus 2 sigma cos theta E over R. Okay, but we also know that PA is equal to P. Hold on. Sorry. We also know that P naught is equal to PB. So we can easily relate PA to PB with the hydrostatic pressure. Okay, so again, we get our Jurin's law. Okay, so the only thing we have to do is calculate this. So this is the radius of curvature at the right. So we say that's a spherical cap. So and this is something that you have to convince yourself of because it comes up over and over again in these problems. Okay, so we've seen the same thing by using this pressure argument. Again, we can get the pressure at A by coming across here, starting at atmospheric, and then getting the hydrostatic contribution, which is this, or we can get it by stepping across the interface having this curvature. And the last, so we've got it from energetics, pressure, and now we can get it from a force balance. So consider the force balance, what's actually supporting the weight of this. Let's do a free body diagram on the meniscus. We know that it has some weight. Gravity wants to pull it down, but the surface tension is supporting it. Okay, so the weight of the column so that's the weight, that's this weight. Has to be supported by something. So what's it supported by? It's supported by the vertical component of the surface tension. It's basically pulling in this direction, so we have to okay, so this is so basically we have this, we have to integrate the vertical component of the surface tension around the contact line, right? So it's going to be 2 pi r and then sigma LV cos theta. So you can also subtract this minus that, right? So it's basically subtracting this tension minus this tension, but that's equivalent to this, right? So it's basically the imbibition parameter, right? Okay, so this is the so that's the vertical tensile force acting on the contact line. So again, we see the thing will climb provided the imbibition parameter is greater than 0. And in all of these, in general, in fluid mechanics, there are these different ways of approaching things. So through energetics, through forces, through pressures. And I always think that you never understand a problem unless you understand every single perspective on it. There are some problems in which it's much easier to understand from one perspective than another, but it's always good to try to understand it from all the different angles. Okay. Any questions? No? So we'll do the dynamics tomorrow. So basically describe, Monday. So look at the dynamics of capillary rise, and then we'll get on to some other things a little more interesting.